I welcome you all. This is a MedBix webcast. My name is Ramana Annamaraju. I'm the host. So I'm not Albert Einstein. My guest is actually female version of Albert Einstein. so so this is a with this broadcast and the webcast is encouraging people to participate in is a diversity of thinking. Diversity of thinking is not an organizational structure. Diversity of thinking in all aspects, to learn the physicians, to learn mathematics, physics, chemistry. Of course, they know already chemistry, arts and technology, all those things, philosophy and psychology, all of them are important. And the understanding that human aspect of it will allow to, to invent, it helps you innovation. That is my goal. So this broadcast is really taking off. Thank you, Dr. Leah Houston. Gave me an excellent compliment. She's an awesome program. She participated in my one of my broadcasts. As you know, I have an accent. Still, the content is more powerful. So I hope so. So anyway, this is I'm going to introduce you my the guest. She is a you know out of the charts her educational background. They can tell you she's a physician, astronaut, aquanaut, scientist. I don't even know what is Aquanaut is. We'll ask her what she does in Aquanaut. She's a taekwondo champion. Don't mess with her. And she does space medicine. Um, you know, then there is why I think it is just a wilderness medicine. I never heard that. These are the extreme medicines. Extreme climates. How do you the medicine work? I think we definitely is very interesting. I'm a physicist. I have a physics background. I have a master's in physics and master's in nuclear engineering. I did a nuclear engineering and computer science, but never that kind of. I spent 30 years in healthcare, but also I grew up in Canada, and then let me bring her to the table. Welcome. This is let me bring Dr. Pandya to the stage. Okay. Welcome, Dr. Shawna Pandya. I
Hello.
wanted to ask you,
Yes. Yeah.
born in a tundra, ice tundra, how a brown girl became a space explorer. That is very interesting.
Yeah, you're right. It's very cold here right now. I think the low today was minus 27 degrees Celsius, which is also very cold in Fahrenheit. Yeah, you're asking about my origin story. So I'm a scientist astronaut candidate with the International Institute for Astronautical Sciences. I haven't been to space yet, but I hope to someday. And like so many other kids out there, it started with a dream as a kid. I wanted to be an astronaut growing up. And I just never grew out of that dream. And I was lucky enough to be growing up in the 90s when Canada's first ever female astronaut, Dr. Roberta Bondar, flew to space. And so I said, okay, well, she's Canadian, I'm Canadian, she's a woman, I'm a woman. So now all I need to do is go be a neuroscientist, physician, and astronaut, and that will be my path. And so that's what spurred me to study neuroscience. I did my master's in space studies at the International Space University. And that's when I really realized for the first time that you could actually make space medicine part of your career. And we can talk about what that field is later this hour. And then from then I went on to complete my medical degree and never really lost that appetite for human spaceflight. I had some amazing opportunities along the way. I was lucky enough to intern at the European Astronaut Center through the European Space Agency as part of my master's internship. I worked with their crew medical support office, and later on I interned at the NASA Johnson Space Center through an aerospace medical elective. So that space bug was there the whole time. There were lots of adventures, and it started off with being a kid. And it started off doing lots of outdoorsy things, going camping and seeing these amazing night skies and thinking, I want to be out there.
Shana, your credentials are just out of the charts for us, even for your intellectual. You're one of the things that I wanted to ask you about the space is you worked on a project called Possum. It's a very interesting. I
Yeah.
want to tell you, mesosphere is probably mesosphere is as close as you can get in the Alberta. I went to school in Alberta.
Oh, you did.
I did. Yeah,
Wonderful.
I went to school in University of Edmonton for a short period of time. I experienced your cold. I don't want to do that anymore.
Yeah,
but
yeah, it's pretty cold up
explain to
here.
me your science about the mesosphere is as cold as probably Alberta. Tell me about that mesosphere.
Yeah, so that's actually the origin story of how this whole scientist astronaut candidate moniker came up. And so, how I got involved with the being a citizen scientist astronaut candidate is I started off training in neurosurgery before I ended up in rural emergency medicine. And when I was transferring into general practice, I had put on my space dreams on hold for a very long time. And I thought the first thing I want to get back to now that I have time again is space. And so I saw one of my colleagues had joined this program called Possum. And what you'll quickly learn is that everything in the space world and the exploration world is an acronym. So POSSUM stands for Polar Suborbital Science of the Upper Mesosphere. And the whole idea of this program is that they would send citizen scientists up to the upper levels of the mesosphere, 50 to 83 kilometers above the Earth's surface, to get more information and data about these things called noctilucent clouds. And so there's this relatively new type of cloud on the meteorological phenomenon. They've only been described since the mid to late 1800s. And they're thought to be a marker of climate change because they become more prevalent and are occurring at lower latitudes other than polar regions. And so we're seeing more and more of this new type of cloud, this noctilucent cloud, also known as a polar mesospheric cloud. So we need more data. And so with Possum, the idea was we would send these scientists up in suborbital flight to get more visual data, more atmospheric samples, to analyze the composition of these clouds and see what exactly is the relationship to climate change and how will this inform our knowledge of upper mesospheric changes secondary to global climate change.
So there is a relationship between these clouds, the strange clouds that you're saying, that
Yeah.
those are all and the climate change. That's interesting that you study about those clouds. Is that, if I'm
Yeah,
understanding?
it's like a canary in the coal mine because it's the first one of the first indications that hey, is or not one of the first indications, but it is an indication that climate change is progressing. And examples we've seen of that is that typically these polar mesospheric or noctilucent clouds they happen in polar regions, hence the name. And they happen at certain times of the year. And what we're seeing now is that they're actually coming down from the poles and coming down to lower latitudes, and they're happening for longer periods during the year. So they're becoming more prevalent. And the link between climate change and noctilucent clouds is that the thinking is that with increased water vapors being trapped in the atmosphere, this creates a layer of ice crystals that seed the upper mesosphere, and those upper mesospheric ice crystals form the basis for the seeding and the formation of a noctilucent cloud. So it's not your typical greenhouse gas. It's actually water, increased water emissions as a byproduct of increased greenhouse gases that forms the basis of a noctilucent cloud.
Interesting. Now you went to space and you were talking, you were reading, you were studying about space. Now let us go to the Aquanaut, the marine side of that thing. You went from all the way to the top to the bottom. Tell me about that Aquanaut. What is your experience about that, and what do you find? What kind of things you find in that Aquanaut training?
Yeah, so when we talk about an aquanaut, we talk about someone who has lived and worked underwater and they've breathed the same higher pressure air that exists underwater. So it's the technical definition is someone who's breathed the same ambient air pressure as the surrounding water around them and who's been in that environment for more than 24 hours. And so that's the technical definition, but the layman's answer is that it's someone who lives and works underwater. And the relation to space is when we talk about how that type of environment prepares us for this high risk, austere, isolated, remote environment up in space. We actually have this saying in the exploration world, same but different. And so when we talk about being an aquanaut, we refer to that environment as being an analog environment because it's analogous to the space flight environment. It's remote, it's isolated, it's resource limited. So there are some parallels there. And so when we say same but different, it reflects certain aspects of the space flight environment. So I went down in 2019 with a crew of 5. We lived and worked underwater for 5 days. We were 2 Canadians, 3 Americans, and we performed all sorts of science related to physiology, psychology, and also tested brand new technologies, which includes my work with Luxsonic, which was my first encounter with the company, and the rest, I guess, they say, is history.
Very interesting. You know that what is that these are all different kind of medicines you're talking about. These are different fields. Even a lot of physicians may not know. Even there's a wilderness medicine. What is that? Wilderness medicine is.
Yeah, wilderness medicine is the branch of medicine that looks at how do you treat injuries when you're away from your creature comforts and the typical medical facilities you may expect to have. And so it pares down medicine into looking at, yes, you can assess, you can diagnose, and you can treat, but you're very resource limited. So how are you in turn going to be creative and resourceful to be able to treat a patient? So there's entire fellowships dedicated to this. There's entire conferences and societies dedicated to this. And it's, it can be, wilderness medicine comprises everything from, breaking a leg while on a hike in the forest and using a tree branch to make a splint, to being creative and using your clothes and the materials you have at your disposal to make a Band-Aid or figure out a way to make a stretcher to carry someone out of a difficult situation. But the whole philosophy is not every arena is going to have the full capacity of a tertiary level hospital, but medicine happens wherever people go. And so, one of the organizations I'm involved with says wherever humans go, medicine must follow. And that's basically the philosophy in a nutshell.
Shawna, if you go to the mesosphere, is there any relationship, anything space medicine you do on a zero gravity, microgravities, or is there anything that you do also some studies in that mesosphere or in polar region about the medicines related to medicine?
Yeah. So for those who don't know, when we talk about space medicine, what that entails, so often I get asked, like, how are space and medicine? How are those like terms? And my short answer is that space is trying to kill you because the space environment is quite hostile. When we talk about the challenges of being in space, we just talked about what it means to be resource limited and confined, whether you're an aquanaut or whether you're practicing wilderness medicine. But you're also in the zero G or microgravity environment. So if you're in that environment for a long time, every single bodily system is affected. Your bones lose density, your muscles lose mass, your fluids shift upward, your inner ear gets confused. There's increased radiation. The further out you go, by the time you're out at Mars, there's a 2-second communication delay round trip. If you're in Mars, there's a 46 round trip communication delay when the 2 planets are aligned the furthest. So there's all these considerations in the spaceflight environment. So even when you think of something as short as a suborbital flight, which is 3 minutes of microgravity, we can start collecting answers even during that short flight. And so we've even seen during parabolic flight where we don't necessarily go to space, but we fly zero G. There's all sorts of studies that, and answers we need about how does the human body react? How does the inner ear react? What changes do we see happening in the cardiovascular system? What happens to vital signs and heart rate variability as we transition in and out of zero G and hypergravity? So regardless of the duration of microgravity, even in the 3-minute period of a suborbital flight, there's a lot of science and a lot of space medicine research to be done.
And also, you will find the suborbital space or mesosphere or above that. The medicine that you do also, it accelerate the discovery of drugs, right? Pharmaceutical drugs. You can find it. I did a just small program on space medicine, a lot of protein growths and all those things. Explain a little bit, if I explain to our audience a little bit.
There's this rising interest. Yeah, that's a really great question. That there's this rising interest in leveraging the microgravity environment to say, how can this help us? And that includes for manufacturing. There's interest in using the micro G environment for semiconductors, for fiber optic cables, and also for drug development. And so when we come back to these crystals that you were talking about, in the 1G environment, crystals don't grow evenly because they have that 1G gradient in force, whereas crystals in the 0G environment can grow larger and more spherically than they would on Earth. So there's thought to be advantages to being able to manufacture in 0G.
So, when you go to the space, it's a microgravity, but when you go under the water, it's a basically enormous pressure, right? Is that the pressure create? So, what are the things you come out of the pressure medicine in that? What are the things that in the diagnosis or treatment or discovery of medicines? What do you think
Yeah,
in the
that's a great
marine side?
question. So the further down you go, the deeper you go, the more pressure there is to contend with. So for our Neptune mission, we were at the Jules Undersea Lodge, which was 20 feet of water. So it's actually not all that deep. And for most purposes, the pressure isn't considered to have a huge effect. That being said, we still noticed in very little subtle things, like the food that we brought down with us, little chip packages, they would scrunch down at 20 feet. The foam in our shoes would squish down at 20 feet. Physiologically, we noticed it. We differences even at that depth. And then where NASA sends its astronauts to become aquanauts is called NEMO, or NASA Extreme Environment Mission Operations. And that underwater research facility is called, it takes place at the Aquarius Reef Base, just down the road from the Jules Undersea Lodge. So both are at the Florida Keys. They're only 13 miles apart. But Aquarius Reef Base is 60 feet underwater. So there's a lot more pressure all of a sudden. And so physiological effects that we studied during our mission included cognition and processing time,
Yes.
performance, concentration. We looked at stress levels. We looked at psychological resilience and well-being. So there's regardless of the depth, there's always lots of science to be uncovered, and the deeper down you go, there's more considerations. And so anyone who's a diver out there will know that once you're at depth for a certain period of time, you need to ascend slowly. Otherwise, you risk a dive injury, because the bubbles that are in solution in your bloodstream will come out too quickly and cause emboli and lodge in bad places like your brain or your lungs, and it can, in the worst case scenario, cause seizure, coma, or even death. And so when you're at depth as an aquanaut, if you don't ascend at a set rate, you're putting your life at risk. So when you talk about decompression periods at the Jules Undersea Lodge at 20 feet, there was no set decompression period because it was close enough to surface pressure. When you're down at the Aquarius Reef Base, you actually have to wait 16 hours and 47 minutes before
Mhm.
you could surface safely. And so when you compare that to the International Space Station, suddenly it makes sense why you would use that place as an analog for preparing astronauts for space. Because if you have an emergency on the space station and you command an evacuation and escape in a Soyuz space capsule down to definitive medical care on Earth, it can be as little as 3 to 6.5 hours. So compare that, 6.5 hours from space to nearly 17 hours from 60 feet underwater. So that's the value of an
Mhm.
environment like the Aquarius Reef Base for preparing astronauts for space.
So, now we talked about physical stresses of the in space and the underwater, and what about the psychological pressures they feel? Can you explain that a little bit? People don't understand what psychological pressures they have in space, and there was a movie. Brad Pitt did that one movie actually under the
Badass.
under yeah under the under the sea, under the water. What are the psychological pressures they face, and what are the cognitive situations there?
Yeah, that's a great question, and it's a really important one because when we talk about the big five challenges of human spaceflight and long duration spaceflight, we call it the RIDGE framework. We talk about radiation, isolation, and confinement, which is what you're talking about, and then things we've mentioned already. So distance from Earth, altered gravity, and everything else, which includes exposure to lunar dust. So coming back to your question about the psychological challenges of the spaceflight environment, these are numerous, and so this includes everything from being in this closed, confined space for months at a time. So you're away from your family, your loved ones. If you want to go outside and get a Starbucks, you can't do that. You have to be a good teammate. You have to be one who works well with your team, but also works productively on your own. You don't want to be that guy or girl who's voted off the space station. You have to be able to deal with a very operationally heavy schedule. So on the International Space Station, the operational schedule is scheduled down to the 5-minute mark. So that's how rigorous things are. You need to know a multitude and be able to perform well across a series of domains, whether that's science, whether that's engineering, whether that's operating a robotic arm, whether that's being able to perform a spacewalk, whether that's being able to communicate your science and do outreach with schools. You have to be a master of your trade, but also a jack of all trades. And then the other thing that we don't think about is the day-night cycles and sleep, and how that contributes. So it's loud on station. So there's always distractions. There's mission control to respond to as well. And then when we talk about how the day-night cycles flip up on station, the International Space Station completes an orbit every 90 minutes. So every 90 minutes, there's a sunrise-sunset cycle. So 16 sunrises and sunsets per 24-hour period. So you can imagine that really must interfere with one's sleep cycle. And it depends on where you're going. So if you're going to the moon's equator, the lunar day consists of 14 days of day and 14 days of night. So there's all of these little things that keep piling up to potentially adversely affect one's psychological health, and that's why it's prioritized as a key area for long duration spaceflight.
You're truly an inspiration for everyone, particularly young women. But I'm going to ask you about the venture that you virtual reality. I will be after I present my topic, and I'll be
Sure.
talking about that your venture about the virtual radiology. I've been involved. I've been involved in the radiology for a long time. I used to own imaging center in Atlanta, and I did a radiology side quite a bit extensively. I participated. I will ask you. Then I saw that little bit of video of that. It is an amazing, and I wanted to ask you once I get back on the after presenting this one, and how do you can watch with me the presentation. But I
Sure.
will ask you what are these venture that you are involved with, and what do you do with that venture? Okay, let me go and present my topic, and you and me will watch together, and um, yeah, just a minute. Yeah, that's a mesosphere. I will ask also one more question. I will ask her when I get back about the suits. The space suits. She does evaluate the space suits. I understand, and see that where we can buy those kind of things or not. We'll ask that again. Okay, but anyway, this is mathematics of the plastic surgery. This is my topic today, MedBricks topic. I will explain what is the mathematics. In 2015, 2013, I think, there was in Korea, there was a contestant, Miss Korea contest. In that contest, all of them, they looked very similar. I thought they looked same. But don't take my word. I'm not the expert. Everybody thinks all the Indians look same, or all the blacks look same, or all the Chinese look same. But the Korean press said that they don't look same, they look eerily similar. That's what they said. The reason was very interesting. They found out the funny part about this, why they look so similar. They went to South Korea as the capital of the plastic surgery. They went to a clinic, similar clinics like this. It's called a Gangnam Golden Ratio Plastic Surgery. It's actually a clinic. Is the name of the clinic. It's a Gangnam is a dance, the guy, Sai guy was introducing. It's a golden ratio, is called a golden ratio plastic surgery. I will explain to you what in Busan, actually, my older brother who lived in Canada, who used to do the nuclear reactors in Busan. In fact, he was installing Busan nuclear reactor in Busan, South Korea. He lived there for 10 years. He passed away recently. But that is the place this clinic is located at. They went to the same clinic and they want to look like a Hong Kong model. So they all carved out the same, exactly same. So that's what the South Korean press was telling. They all looked exactly eerily similar. But what is this golden ratio? This golden ratio is like if you have if it's in the plastic surgery side, golden ratio is if you have a upper lip is 1 centimeter in the lower lip, or beauty. So is a 1.6. That is what the some ratio they maintain that between the among the body structure. That's what they do. It applies to entire body. Actually, the golden ratio they can apply to the length of the face and against the width of the face, the nose and the eyes, all kinds of things you can apply entire golden ratio. I will explain where it came from. So the upper lip is 1 centimeter. Suppose if you have the lower lip should be 1.6. That is a mathematic. The golden it maintained that is a golden ratio. 1 to 1.6 is a golden ratio. So to the most of the plastic surgeons follow particularly in South Korea, they followed that process, and that's why all the lips look same, all the eyes look same. That's one of the golden ratios effect. So you can apply this golden ratio to the entire body. That's what they do in some countries, China and Korea. So they came out with what they found out is the perfect body for the actress. Actually, for the golden ratio, perfect golden ratio is the Helen Mirren. She is a British actress. She has a perfect body. I don't know about that, but that's what the science said. But actually, it came from the Greek sculpture. That is a Phidias, is like a Greek mythological figure. That's what they say is a perfect figure. Is a height is like 6 feet, suppose, and if he has 3 feet in the from the top to the navel side, and the navel to the feet is a 3.6. Sorry, yeah, 4.6. It should be. I made a mistake. So there is a 1.6. Yeah, 3.6 actually. Yeah, I did right. I think 1.6. Yeah. So studying too much math is not good. But anyway, so that is a golden ratio. That is a Phidias from the Greeks mentioned about the golden ratio. But let us just put aside a golden ratio. We will find out where it came from actually. Leonardo Pisa is a Italian born. Is in 1170. Is a 11th century, 12th century mathematician. Is actually merchant. His father was a merchant. He was. His name is also called Fibonacci. Is actually his name is Leonardo of Pisa. He is from the Leonardo of Pisa. Pisa is a county, I think. Is a city, possibly. But is actually his name is now after that referred as a Fibonacci. He was in the 1170 was born. He was going from Sardinia, part of the Italy, is the coast of Italy of Sardinia, to is going to Africa to get the merchants to do the actual get the products, for the trading. They are the merchants, naval merchants. His father was a merchant. So they used to go to the northern Africa to get is a 200 miles journey from there to there. And then they used to meet people from Indian traders there, or Indian goods there, like spices and the gold and silver, those kind of things. They used to see that. So the Fibonacci never went to India, but he used to meet them, or he used to interact with the merchants who went to India there. That is a very. So then what he found out is very interesting. What he found out there is a curiosity, a curious mind. He's a navy merchant. His father is a navy merchant, but Fibonacci has some interest. He At that time in Italy, they were following in Roman numerals, like that strange numerals you see all the times, fourth, George fourth, and all those things. They were following Roman numerals. But when he went to Northern Africa, which is Algeria, actually now it is called Algeria, he found something interesting. It is a Hindu Arabic numeric system. They have first time he saw 0, 1, 2, 3, 4, 5, 6 with a different connotation, but the notion, the Hindu Arabic numeric system was seen. He experienced it there. All the merchants are doing the Hindu Arabic system, not the Roman numerals. That he fascinated by that. Why it is so easier. For example, if you see 99,000, the way it represents in Roman numerals are way longer. It's much easier. It's outrightly easier. How it came out. So it came out that in Pingala, the Acharya Pingala, is a second century, third century scientist, mathematician. Pingala invented a zero. It's called Sunya from India. It's called Sunya. Sunya is a zero. So that was, he invented zero. That is there is an evidence there in the temples. But actually there was other places also invented zero. In the Mayan empires and Chinese, they were talking about zero. But the real turning point is at the 6th century happened. His name is Brahmagupta. He was a mathematician. He put a place value. He is the one, he did put the place values that he did in the mathematics. 1, 2, 3, 4, 5. You see 10, 100, 10 to the power of 1, 10 to the power of square. These are all the place value created it. That changed the entire system. That is the power of the mathematics he created. That is a widely that was caught the attention of the Fibonacci. So he went back to Italy and he wrote a book. The book is called a Liber Abbasi. Liber Abbasi is a book of calculations. In this book, he talks about Modus Indaram. Is a method of Indians. He talks about is a first book on math. Is a Western math book. It is. So it was a popular book. So in that book, he talks about a lot of Arabic numeric system. Actually, that went on a wildfire and into the spread across the entire West Coast and entire East, in the entire Western Europe and Europe itself. So Fibonacci also found a strange sequence. You put the numbers like 0, 1, 2, 3, 4, 5. As you know, what he do with a sequence, he found out very interesting sequence. If we add the previous numbers together, so 1 plus 0 plus 1 is 1, 1 plus 2 is 3, 3 plus 5 is 8, 8 plus 13 is 21. If you add the previous two numbers, the succeeding number is the last, adding the previous two numbers. That's called a Fibonacci sequence. That you can go 34, 55, 89, just you can keep on going like that, the number. So what is special about these numbers? Why anybody, it doesn't make any big sense, just by adding two numbers. But what they found out is very interesting. All the flower petals, you see that they follow the Fibonacci sequence. The flower petals 2, 3, 5, 8, 13. These are the Fibonacci sequence numbers it follows. So nature follows the Fibonacci sequence, and the nature adopted somehow that he found out the nature's secret, in fact. So not only in that, you can find in the corn spirals, you see that a lot of plants, and you see that leaves and some of the corn spirals. One way it is 34, other way is 21. The spirals, you count them, they follow Fibonacci sequence, Fibonacci numbers. So Fibonacci numbers, sunflower, that is, for example, follows the Fibonacci numbers. That's a very interesting. So the nature has embedded some kind of a Fibonacci. It's following Fibonacci sequence, not following Fibonacci sequence. He found out that sequence, that is nature's secret. So then, when you take these two numbers and you divide the third number into the previous number, not in the first few of them, after that it becomes a convergence. I don't want to get into the mathematics, but if you go to for example, if you have 144 divided by 55 is always 1.6, that's where the golden ratio pops up. Very strange as it is, the golden ratio pops up at the when you divide the succeeding numbers, any numbers in the from the all the way to the infinity, you can do that. If the two numbers, you take the succeeding number, divide the previous number, it is a golden ratio 1.6 will show up. That is an amazing. It's a so that is the Fibonacci golden ratio came from the Fibonacci sequence. So that is the golden ratio. That is the convergence. So Fibonacci retracement, this is one of the stock markets. I don't have much clue about that, but they use this Fibonacci sequence. How the stock market falls, it follows the Fibonacci numbers, Fibonacci sequence. There were tools available. Day traders follow Fibonacci sequence like a Bible almost. So I didn't know that, but it is very interesting that somebody can talk with us about that. I'll find somebody who can. That's a black kid up there. He talks about three chapters about the the Fibonacci retracement. You can watch on video on YouTube. But the golden ratio is, as you see, 1.1 is a 1:1 is ratio is a 1:1 ratio is equal number. 1 to 1.6 is a little bit bigger. That's what they followed in the Fibonacci numbers. You can see that is always, you can see in the hand, actually hand itself, the bones follow the Fibonacci sequence. If you see the numbers you follow, actually the length of each the bones in the from the wrist to the all the way to the finger top, it follows the Fibonacci sequence. That is, nature has that. So Fibonacci found a sequence. Some natures, he discovered nature's secret. So if you want to find out ancestry, for example, you go all the way to the. If you want to meet your Neanderthal parents, you can. If you go back all the way to the Fibonacci sequences, you can find the long way back. You can see what generation, what number is previously can go, which generation you have that strange parents you have. That you can give. Fibonacci sequence can give the ancestry part very well. But the next one is blows off your mind, actually. Detecting cancer, particularly breast cancer. If you take a Fibonacci sequence and you correlate into the matrices, what he does is, for example, they do by measuring the temperature on the breast cancer, on the lumps. So I used to work with a lot of radiologists, and one of the things is that calcification looks very suspicious. We can ask Shawna about that. So that she's a doctor, she can tell us about that. So the calcifications, what it does is, so they go and do the biopsy, and when they do biopsy on it, what it does is that it creates a more scar tissue, and then next time when they come back to the next year, then it looks much more worse, and then they do another biopsy. It's a keep on getting worse and worse. That is a problem with these biopsies sometimes. So in Fibonacci matrices is very interesting. Without a biopsy, you don't have to touch anything. By measuring the temperatures on the lumps, on the surface of the breast, you can come up with the matrices. You can come up with a quantifiable number. It's called a mu. If it is a more than a zero point 0.7, that is a malignant. If it is a less than a 0.7, it is basically a benign calcifications. They are very interesting, right? So Fibonacci, you think about a 12th century mathematician, how he's helping us to find and detecting the cancer in the people. That is, these are the true scientists, true mathematicians. People like Shawna will really contribute to the world so much. We are actually praying at demigods. We need to be really admired. People like Shawna. Let me bring her and ask her bring her back to the table. One second. So how do you like Shawna?
Yeah, that was definitely outside of my own field of expertise. So I thought I learned a thing or two here.
Thank you. But it is I bring like a mathematical. Yeah, a lot more than everybody else. But it's I wanted to bring a little bit of different fields and then interdisciplinary field to the medicine. So you do that all the times. One of the things you are doing, that is, this is you are involved with what do you call, a virtual reality radiology training program. Tell me about that, a little bit about it.
Yeah, so this was the technology that I mentioned when I was talking about some of the technologies we tested on our underwater Aquanaut mission. One of the things we brought down with us was this virtual reality headset. And the reason was it housed this medical technology, the world's first virtual reality radiology reading room. And I, as the crew medical officer, definitely had an interest in medical technologies for austere environments, as we've been talking about this hour. And so the benefits, why do that? What does that even mean? So just to back up a step, when radiologists read images, whether it's an X-ray, a CAT scan, an MRI, it's really a fine-tuned process. It's they need a very delicate setup of high-resolution monitors. They need their dictation software. They need a secure cloud server on which to be able to store the images. So this physical setup actually takes tens of thousands of dollars. It takes a lot of physical space. As you can imagine, not everywhere has the infrastructure to house that level of radiology setup. And so definitely on our underwater mission, we didn't have the space to set up a radiology reading room. But it's not just underwater. Across the world, there's so many medical, rural, remote cities, villages that need access to health diagnostic imaging. And so the CEO of the company, my boss and a good friend, said, well, what if we could leverage the power of immersive technology, specifically virtual reality, to recreate that workflow in virtual reality. So then if you're a radiologist, you can read images, you can deliver that critical piece of healthcare to patients, regardless of where you are, how little space you have. And so that thus was born the company Luxsonic and this product Sievert. And so basically you put on the headset and suddenly you have access to your full slate of tools that you would as a radiologist. So to give you an example, when I was underwater on this mission, I took the headset with me and we did a simulation where we had a trauma and we had to image the patient. And so we had this comminuted scapular fracture of the simulated trauma patient. And I was able to meet up in this virtual reading room with the head of radiology in Canada, in Saskatoon, over 4,600 kilometers away, to review this imaging and the key findings. And so imagine, you don't have to be underwater to appreciate how useful this is. I work a lot of rural emergency as well. And so I'm often in need of a specialist to say, hey, can you review the key findings with me? This broken forearm, does it need to be reset? Is it too displaced, too angulated? So you can recreate all of that critical workflow, collaboration, expert consultation in this virtual space. So that's the origin story with Luxsonic, and that's what we aim to do. And we've also developed a virtual reality training and certification platform for medical and healthcare professionals to train and practice critical procedures and skills in virtual reality. And then the space connection there is we've built modules for the Canadian Space Agency to be able to practice skills in virtual reality. So they don't have to bring all of their hardware, all of their setup, all of their tools to practice skills, so they can still keep up their skills on a long duration space flight, even when they may not have all of the typical physical architecture they would need.
Truly amazing. I've been involved with the radiology for a long time. I'm not a doctor, but I've been involved with radiology equipment. I ran the imaging center. But I tell you, so you're saying to me, you can diagnose actually the on this virtual reality set, you can actually diagnose it.
Exactly, yeah. So with most commercial headsets, the resolution of images for your day-to-day X-rays and CTs is good enough to, when compared to the traditional physical setup, to be able to read with the same resolution and accuracy. We've run several trials with our academic partners. The really Mammography is the one exception to that. That tends to need higher resolution and need some higher end headsets. But for day-to-day x-rays, your commercial off-the-shelf Oculus or HTC or your Vario headset, whatever you have, it will support medical and diagnostic care.
Tell me the process between once you've taken the image from MRI or CT scan or just a plain X-ray, how do you move that into the virtual reality? What is the transformation process involved?
Yeah, so for the technical details, I would have to refer you to our
Okay,
CTO.
just yeah.
Yeah, but we
I'm
do
not trying to
replicate
put you
the secure.
on spot. Yeah.
Yeah, we do replicate the secure PAC server and the secure cloud storage that you would have in a traditional radiology workflow.
I didn't know that. It's truly amazing. You can diagnose, so you can empower a lot of radiologists from a small
Exactly.
towns,
Yeah.
rural areas. I went to Regina. Even in Canada, I've been to Regina, Saskatchewan,
Yeah.
Saskatoon. All even small towns like in my hometown in India village, my father used to practice. So you can empower them with this virtual reality set. They can literally see the radiology images from there. Is that what you're saying?
Exactly. We can bring diagnostic imaging to anyone, anywhere, anytime, as long as they have a headset, and we bring the back-end infrastructure with us.
Very good. I wanted to so thank you. That is an amazing venture, and I love to be help and involved anyway. You guys like it, but it is a truly an inspire. That is a totally mind blowing in my view. But I wanted to ask you. The question is that you're doing. What is the next steps on the think of what are the new frontiers in the space medicine or marine medicine or wild wilderness
Wilderness.
medicine.
Yeah. Yeah.
What do you think? What are the new
Yeah.
things, new frontiers?
There's two major horizons in space medicine, and so there's the near term and then the very far term. They're actually almost at opposite ends of the spectrum. So one is the rise of commercial space. So we talked earlier this hour about suborbital flight, and so we're seeing what we mean by commercial space is suddenly it's not just NASA astronauts who get to go to space. And so the difference is NASA astronauts are very, very highly selected for health, for physiology, for psychology. They're the best of the best. And so when we open up the frontier so that anyone who wants to go be a spaceflight participant, go be a space tourist, anyone who wants can go by a ride to space, suddenly we have a change in the health profile of who's going to space. So as we open up frontiers to access to space through Blue Origin, through Virgin Galactic, through a whole host of emerging space companies, now we have to say, well, when we're not sending the healthiest of the healthy to space, how does that? How does the challenges of the spaceflight environment that we talked about this hour? How does that impact the everyday physique and physiology? So that's the one end of the horizon of what's next in space medicine, and then the other is the far off destinations. And so when coming back to space agencies, the international community, NASA, the Canadian Space Agency, ESA, the JAXA, the Japanese Space Agency, have their sights set on long duration space flight and exploration class missions. So NASA has very firmly said that we're going back to the moon and we're going back to stay. So that means it's an international undertaking. It's a very, very challenging undertaking. So there's a lot of international cooperation required. So coming back to what's on the horizon in space medicine, when we look to far off destinations like the moon, it's realizing that we can't evacuate back to Earth if we have a major medical issue. The moon is 2 to 5 days away. One of the goals towards going to the moon is using it as a test bed for Mars, which is 6 to 9 months away. So now imagine you have a critical medical event on Mars. How do you empower your astronaut crew to be able to be autonomous and treat critical medical issues in situ? So along with that comes emerging technologies like virtual reality and immersive, like we talked about, for skills maintenance. 3D printing to acquire tools that you may need, AI and machine learning to help support diagnostics. So there's so many emerging technologies that will need to help empower us to just not just survive, but thrive on the moon and Mars. So when I say there's two horizons for space medicine, it's commercial space and exploration class missions.
Can you shed some light on the spacesuits? What are what is it about spacesuits? What are the commercialization of the spacesuit? Because a lot of people are going to go to the space now with the Virgin Galactic and the Blue, all those things. So, what are the things involved with the commercializing the spacesuit, and how do you monitor the quality and all those things?
Yeah, that's a great question. So you had a nice image of that EVA extravehicular activity spacesuit up on that on the possum slide. And
Yeah.
so when I say in space and exploration, everything's an acronym. So when we talk about spacesuits, we talk about EVA and IVA spacesuits, and the difference is EVA is extravehicular activity spacesuit, so outside your spacecraft, and IVA is inside intravehicular activity spacesuit. And so the reason we need it's pretty intuitive as to why you need a spacesuit outside of the space capsule. You need to protect it from the extremes of the temperature, the vacuum, the radiation, debris. So it's obvious as to why you need an EVA spacesuit. Yeah, that's the one. And then inside your spacecraft, especially on launch and landing for orbital missions, you wear an IVA or intravehicular activity spacesuit. And the reason is in case that there's an atmospheric compromise in your spacecraft or launch vehicle, you have a secondary mini spacecraft in the form of your IVA spacesuit, which you can put the visor down, pressurize, and have a habitable life support system within that suit. So to your question about how does that impact suborbital flight and Virgin Galactic and Blue Origin, these commercial companies are very committed to making spaceflight safe, comfortable. They want it to be more like commercial air travel. So we don't need any layer of protection when we fly on a transatlantic flight from New York to London, say. And so it's the same kind of environment that's been recreated in suborbital vehicles. They say it's so safe your grandmother could fly. We call that a shirt sleeve environment. And in fact, even NASA astronauts, the astronauts on the space station, once they have completed their docking maneuvers with the space station, they're not always wearing their spacesuit inside the space station. If you look at videos of astronauts on station, they're in comfortable clothes, they're in shorts, they're in t-shirts, they're in pants. So it's really more for the critical moments when there may be a loss of atmosphere or pressure in the launch vehicle. So getting to the last part of your question, you talked about commercial spacesuits, which is right up my alley, because that's one thing that we've been very privileged to do through Project Possum and the International Institute for Astronautical Sciences. We worked with Final Frontier Design to test both their EVA and IVA spacesuits. We've tested them in zero-G, we've tested them in water scenarios. And this comes back to your question of how do you trust your spacesuit? How do you know it's safe? And the answer is, before you can send anything to space, you have to test, and then test some more. And before something can be deemed truly space ready, it actually goes through a series of TRLs. So there's another acronym. TRL means Technology Readiness Level. So for space technologies, this exists on a scale of 1 to 9. 1 might be something that you just, an idea that you just scribbled on the back of a napkin in a bar, so it's concept phase. And 9 is something that is spaceflight heritage and is you can trust to operate in space. And somewhere along the way, technology level 6 to 7 is something that you've tested in a space-like environment, like the parabolic flight. And so way before a technology like a spacesuit makes it to space, it's been tested in all sorts of space and space-like environments to make sure you can trust the engineering of the spacesuit.
What kind of material they use for the spacesuit in general?
Yeah, it depends on the layer of the spacesuit you're talking about. So all of these, the anatomy of a spacesuit is fascinating. So you have outside layers that may be cloth. And in the case of the EVA spacesuit, you have increased radiation protection, for example, on the visor. On the insides of these spacesuits, you may have these coils of liquid tubing to help cool the tube. You may have various new materials and plastics to to on the inside to be waterproof, to be able to seal against the environment. So it's actually a multitude of materials that's used. It depends on the layer of the suit that you're talking about.
These kind of technologies are useful. People think it is only applies in the space and space or some under the water. But I found out recently that in NASA they gave a spin-off for menopause. For a menopause woman, they can use the gloves technology for the variation of the temperatures in their menopause, going through menopause.
Yeah, there's all sorts of examples of spin-in and spin-off technologies. And so when we say spin-off, we mean technologies that have been used for space flight, that have been used to make life better on Earth. And there's lots of examples of medical technologies that have benefited from space flight. So to your point, something similar, the sensors and the sensor suits that were used to monitor astronauts during the shuttle days has been spun off into something called Mama Goose pajamas that have been used to monitor infants at risk of sudden infant death syndrome. So we use space-based technologies to keep babies safe.
I'm so proud of you as an Indian, fellow Indian, and you're truly an inspiration to all young women in the world. I think it's an honor and a privilege to talk with you. I can talk with you hours together. Thank you so much, Shawna, Dr. Pandya.
Thank you so much for having me. It was my pleasure.
Thank you all.
We are retelling their stories through our patented designs that can be worn on scrubs, t-shirts, printed on conference bags, and endless other promotional materials. Daily Wear for Medicine is the first ever of its kind to create curiosity in medicine through visual art. We at MedBricks are celebrating unsung heroes of the past who made enormous contributions to the field of medicine through our unique campaign called Daily Wear for Medicine. You can wear it, carry it, and give it.